Hello, this is Jeremy Zimmerman, and today I'm going to talk about one-dimensional defects in crystals, specifically dislocations. So the reason we're talking about these, again, is crystals are never perfect. And there are two types of one-dimensional defects. There are disinclinations, and these show up in liquid crystal materials. And then the topic of today's discussion are dislocations. So we have to understand dislocations because they're critical for understanding a lot of mechanical properties and how you get um, deformation of materials. So how you get plastic deformation of crystalline materials. This also allows for relieving strain, and it becomes important in things like epitaxial growth and defects that harm semiconductors. So what a dislocation does is it locally breaks kind of the perfection of the translation vector. And the dislocation is going to distort a large portion of the crystal, and it always extends along a line. And this line typically curves around through the crystal, and it either exits the crystal at 2 points or it forms a loop. There are two major types of dislocations. There are edge dislocations and there are screw dislocations. And these represent the extremes of the type of dislocations you can have. You can also have things that are somewhere in between an edge and a screw, and we call that a mixed dislocation. So here I'm showing you an edge dislocation. Very far from the center of this, out towards the edges and the top and the bottom, this crystal looks perfect. But what we've done is we have inserted essentially a half layer of atoms into this portion of the crystal. You can also see that on this image here where we've added this extra half plane of atoms into the crystal. So there is something called the dislocation core, and that is kind of the line that sees the maximum strain. And that's shown here in the blue. In order to define the dislocation, we use something called a Berger's circuit. So the first thing I'm going to do on this diagram is draw the dislocation core here in blue. And then we're going to draw a Berger's circuit. And so we're going to kind of circle the core with what I'll call a square loop. And so I'm going to pick a starting point and I'm going to move, in this case, 6 lattice translation vectors to the left. I'm going to move 6 lattice translation vectors down, 6 lattice translation vectors to the right, and 6 lattice translations vectors back up towards where we started. And what we see is that because we encompassed this dislocation core, we didn't start and end at the same location. So the Berger's vector is the vector that goes from the start of the red arrows to the end of the red arrows. And so we would draw that here, as I've done in pink. This is the Berger's vector. For an edge dislocation, as shown here, the Berger's vector is perpendicular to the dislocation core. So dislocations alleviate shear stresses in the material. So if we look at the upper left here, this material is strained. So we've been applying forces like I'm showing in the red arrows here. And this material is distorted away from its simple cubic normal self. So it takes about an order of magnitude, or many orders of magnitude, less energy to break a single row of atoms, for example, along here, the bonds on that single row of atoms, as opposed to breaking an entire plane of bonds and then letting it reform. So this one row of bonds breaks, and then you get a little bit of relief of the shear forces here. So we've relieved some of the shear forces, and we kind of see an offset at the edge of this crystal. If this progresses a little bit further, what we see is here is kind of we have bonds have reformed here, and we now have this extra plane of atoms inserted into the crystal here. So this looks like our dislocation. If we continue to apply shear force to this material, this dislocation will continue to move. So it moves over one more step here, another step here, and then finally it exits the crystal over here. So this motion that I've been showing in this slide is called glide. Now I want to talk about screw dislocations. So again, the lattice is perfect, very far from the dislocation or the core of this dislocation. So if we look at the left or the right portions of the crystal or the front or the back, it looks pretty much like a perfect crystal. But in the middle, something messy is going on. So you could think of this like a parking deck. So if we were to be in our car up here at the top of this parking deck, and we were to drive down here, and we got back to this location, we'd end up 1 unit translation vector deeper into the crystal than we started. So if you were to keep driving down this, you would eventually go around and around and around, and you'd come out the bottom of the parking deck. Another way of thinking about this is that you have kind of layers of atoms, and you, so like sheets of paper, and you take those sheets of paper and you cut them halfway through, and then you tape them back together, but each paper is taped to the one below it, so it makes kind of a screw. Here I have redrawn this screw dislocation, and I've kind of flipped it over 90 degrees so we can look down the dislocation core, and we can draw the Berger circuit for this dislocation as well. So the first thing we're going to draw on this diagram is the dislocation core. I'm then going to draw the Berger circuit. So I'm going to circumnavigate this core in a square loop again. So I'm going to pick a starting point. In this case, I'm going to go pick a starting point and then go up by 3, left by 1, 2, 3, 4, 5, 6, down by 6, right by 6, and up by 3. And we can see that in this case, the arrows again did not meet up, and that's because we surrounded a dislocation core. So the Berger's vector is going to be kind of hard to see on this diagram, but I'm going to draw it in pink again, and I'm going to draw it from the start of the red arrows to the end of the red arrows, just right here. So this is a screw dislocation, and in a screw dislocation, the Berger's vector is parallel to the dislocation core. And now I have a few things I'd like you to think about. First, I want you to make sure you understand the definitions and symbols for Berger's vectors and dislocation cores, and make sure you understand the difference between an edge and a screw dislocation. I want you to download the 2 Vesta files of dislocations, and I want you to play with them. So I want you to make sure you can see where the dislocation is and understand how it distorts the surrounding lattice. For an edge dislocation, I want you to identify the extra half plane of atoms, and if you move far to the left or right of the dislocation core, as I showed on slides 3 and 4 of this presentation, and you assume that the crystal becomes flat, how are those 2 planes oriented relative to each other? For the screw dislocation, if we look at the orientation as drawn in slide 6, how is the section far to the left or far to the right of the screw dislocation? How are those 2 parts of the crystal oriented to each other? I called this a one-dimensional defect, but I inserted a half plane of atoms. If it's a plane of atoms, why did we call it one dimension? And there are 2 extremes to dislocation types, edge and screw. You can also have mixed dislocations, and these have a partial edge and partial screw character. So what would the angle between the dislocation core and the Berger's vector be for a mixed character dislocation? Thanks, I'll see you in class.